have two speakers and a panelist, and I am your moderator. I'm Rick Riss. I'm a senior consultant at ARC. I cover some of the areas of grid automation functions. I do have a background in process control, and now I'm trying to figure out how to control electrons. All right, and you know, they're hard to get a hold of sometimes, and they move fast. So in any event, actually, I take that I'm not just a senior consultant, I'm director of consulting. So I did get a new title recently. So we will have a Slido poll on here, and if presumably we can make it work. If you can scan this, and it's a pretty simple, trivial poll just to get you thinking about, well, where are all the emissions in the production of oil and gas? All right, and basically all we're really asking you to do is to rank whether most of the emissions are in upstream or downstream or midstream, you know, and it just take 3 items and rank them, and we'll use that as a kind of a kickoff to get involved in our discussion. So it would be very interesting that for the oil industry, you know, why is the oil industry interested in decarbonizing the production of oil and gas? And I think we're going to go through some of the examples. There are regulations, for example, in the UK, that as a condition to operate an offshore oil platform, you will decarbonize that platform. You will stop emitting CO2, or you will not be able to operate a platform in UK waters, right? I think there are also situations where the stockholders had pressured the board of directors, or the board of directors just on their own decided that we're going to have net zero initiatives, and we're going to decarbonize our operation, and therefore have targets to in fact improve that operation. And I think, as we'll see going forward, not every gallon of gasoline you buy had the same carbon footprint, depending on where that gasoline came from and how it got to the pump. So, you know, the oil and gas business is segregated into upstream. That could be both onshore and offshore oil production. Midstream, which is really the transportation and storage, mostly of crude oil. And downstream, refining and distribution of the finished products. So that's kind of how the oil industry segregates their divisions and investments. And occasionally these groups talk to each other, or maybe they're not all in there. A lot of the oil companies make most of their money in the production side of the operation. The vast majority of the cost of a gallon of gasoline or diesel is in the oil that was needed, that they had to buy, that went into the refinery. So I also like to mention that another activity that's underway is this 40 CFR Part 98. And there's a lot of updates to that, and that's an ongoing thing. And I know that TJ might be able to provide a little bit more insight into how this reporting is required. But if you look at this 40 CFR Part 98, there's some 8,000 different facilities that are required to report their greenhouse gas emissions. Now, exactly how the template of where they got the data and how they reported it is in the process of changing to get perhaps a more rigorous, accurate representation, and not kind of cross sections of what typical industry will do. Because I think some of those reports, you know, are not based on actual measurements of how much methane got flared, or how much, you know, how much methane was leaking at this particular flange. Some of those things are a little tricky to know about. And in fact, if you wanted to see a number of templates, you look at all of these different industries, and you can see electric generation, aluminum, cement. All of these different industries are required to report their greenhouse gas emissions in a particular format, and this is an EPA requirement. So you can imagine there's a fair amount of paperwork. There might even be some pushback, but it does seem that the direction we're going into is we you need to know where your emissions are coming from. I mean, the starting point of any kind of sustainability program and net zero program is to figure out, well, what are my emissions, all right? And we'll talk about scope 1, scope 2, and scope 3 emissions, because there's different categories of those. So with the greenhouse gas reporting protocol, for those industries that are required at a certain size to make a report, they're required definitely to report scope 1 and scope 2 emissions. They're optional on scope 3. And then for others, you could also opt in to report your scope 3 emissions. And scope 3 emissions, I think, as we've seen in some of the slides earlier today, even in one of the keynotes, generally tends to be the largest overall within industry. And some situations, one company's scope 3 emissions is another's, scope 1 emissions or something. Right? So what is scope 1, 2, and 3? Scope 1 is the direct emissions from owned and operated sources. Your scope 1 emissions are the CO2 that comes out of any smokestacks you have in your house, a heating system, a boiler, a hot water heater. What comes out the exhaust of your car, that's yours. All right. And if you're an oil company, it comes out what comes out of the stacks and all of the effluents in your power plant. And in a refinery, there's an awful lot of fired heaters. You might be able to make steam or hot oil. You have a fired heater for the reformer. You have there's a lot of stacks. And some of those emissions are not just CO2. It would be methane, CO2, I think CFCs and PFCs, and I think nitrous oxides are considered the main classes of greenhouse gases. Now, scope 2 are the indirect emissions. So your scope 2 emissions would be the emissions caused from the electric power you use to heat your house or charge your car. All right. So scope 1 and scope 2 are the emissions you would be wanting to report. And obviously, in the case of an oil production, if any purchased electric power or purchased fuel would be part of that scope 2 emissions. Scope 3 are all the other indirect emissions that occur in a company's value chain, and some of those emissions will be upstream and some will be downstream, and I'll show you a picture of this. I think this probably gives the best example. You see vertically in the middle, scope 1 emissions. You see on the top the different greenhouse gases that constitute your emissions. CO2, methane, nitrous oxides, hydrofluorocarbons, and perfluorocarbons, and SF6, sulfur hexafluoride. Probably not too many people have that. You'll find sulfur hexafluoride actually in a lot of electrical switchgear as a dielectric. I'm not sure all the other places SF6 might be used. Then you can see scope 2 emissions are also your indirect emissions, and basically, kind of in a small text, it's basically what you've purchased electricity and resources. Then the scope 3 has 2 categories. One is kind of the indirect. That would be the embedded CO2 emissions from all of the things that you would have purchased, all right? And that scope 3 emissions for an oil refinery would be, say, the embedded emissions. If they buy in crude oil, all right, it would be how much emissions did it take to get that crude oil to the refinery, all right? And that would include any of the activities from drilling it out of the ground to processing it and transporting it to the refinery. All of those would be its scope 3 emissions. Then on the external downstream side, your scope 3 emissions would be all of the CO2 emissions that your product caused. Of course, the oil industry, they are producing products that were intended to be burned, and in the most case, they are burned without carbon capture and storage, so there's a lot of CO2 emissions. In the primary CO2 emissions in the oil and gas industry are these scope 3 downstream side emissions. But in many ways, you can't hold the oil industry responsible for those per se, because our entire economy depends on oil, gas, and coal to keep running. So I thought to give kind of an example, some years ago I did some work at a Venezuelan refinery called Syncor, back when I was doing control system engineering work. On the left-hand side, you see a piece of equipment called a delayed coker. The oil that's the oil industry in Venezuela is based on the Orinoco oil field, which is an inland reservoir that has, I think, one of the largest sources of oil in the world. It is, however, a very heavy, viscous oil. It has an API gravity of 8 to 18. Typical crude oil is an API gravity of 30. All right, so it's much thinner stuff. It has lots of aromatics and it has lots of sulfur in it. And so they've actually shipped kind of a kerosene type liquid all the way out to the Orinoco oil field and mix it with this crude oil just so it's pumpable, because it's so thick you can't pump it, all right? And they pump that mixture back to the refinery on the coast, and there's a whole collection of refineries on the coast that all basically make synthetic crude oil. You know, they don't make finished products typically in Venezuela. So that coker is a very common reactor system. This is called a delayed coker. They call it a delayed coker because the heavy, thick crude oil is pumped through a furnace, but it's pumped through it at such a high speed that by the time it starts cracking into solids and coke and other lighter hydrocarbons, it's literally trying to thermally crack these large molecules into a collection of gasoline and diesel boiling point ranges, which are much more valuable than the heavy asphalt type stuff. And it goes through the furnace so quickly that it only starts to react as it exits the furnace and goes into these large coke drums. And there's each furnace has 2 coke drums, and it switches between coke drum A and coke drum B. And once coke drum A fills up with coke, they switch over to B, and then they take some period of time to dump all of that coke out. And in the picture on the right-hand side, you can see on the left, there's actually a large piles of black coke that came out of this delayed coker. And then the cracked gasoline component goes to fractionator, and it goes throughout the rest of the refinery. And one of the processes that is used to make synthetic crude is to, first of all, to make hydrogen in a reformer, which again has to burn CO2 in this endothermic reactor to make the hydrogen from natural gas, essentially. And that hydrogen is then used in a desulfurization process, so another reactor, you know, and in order to remove the sulfur from that crude oil. And you can see the sulfur piled up outside, all right? So in any event, that you could imagine that now the resulting product that they have made at this refinery is in the range of API 30-ish crude oil that with the sulfur removed, and they would send that to, say, other refineries worldwide. You know, we used to buy a lot more from Venezuela, and it would come into the Gulf Coast refineries, which were particularly optimized for this this crude oil, which still had a lot of aromatics in it and other products that had to be dealt with specially. And so basically it is just a crude oil. And you could compare the crude oil that came from Venezuela to the crude oil that came from Saudi, which they call light sweet crude. It's light because of its API gravity 30 already. It didn't have all those high molecular weight asphalts. It's sweet because there was no sulfur in it, right? So you could imagine that if you just had light sweet crude coming into the refinery, or you could choose to purchase Venezuelan crude, you're purchasing a big carbon footprint when you purchase that Venezuelan crude. And there are many other sources of different types of crudes, and I know TJ has educated me that depending on where the source of oil came from, there can be over a 10-to-1 difference in the carbon footprint of that oil. And in fact, there may be some ways of eventually rating this. So this is still, you know, from the Venezuelan point of view, they have a lot of Scope 1 emissions. From the refinery that's buying the crude oil from Venezuela, they have, you know, Scope 3 emissions because it's embedded in their supply chain. Let's jump a little bit. You know, some time ago, I did a little bit of work on floating FPSOs, which is a floating production, storage, and offloading platform. And it came to understand that oil rigs are drilling all the wells and making underground piping that come to a riser pipe from multiple wells that come up to a single FPSO platform. And typical oil and gas technology is there's a combination of oil, water, sand, and gas that can come out of the ground. Well, we didn't really want the sand. That goes back down. The water, we definitely didn't want that. And the gas often would be purified sufficiently to burn in a gas turbine to make the electric power that runs an FPSO. And you may be surprised to learn that FPSOs need a lot of power. They typically are not producing natural gas, and so they need to compress that natural gas and push it back down into the ground. All right? So, and then they need to provide power for pumping and operation of that FPSO. But an FPSO could be in the range of 50 to 100 megawatts of power. You know, my little town of Princeton, we have an average power load of 1.5 megawatts. You know, we're only 3,000 houses, but you know, this is a city worth of power, all right? And of all of the emissions that you might think of on FPSOs, you know, there's going to be a few flange leaks, so methane is leaking. There's going to be maybe a flare there because, you know, there are situations where you need to flare materials. And probably one of the largest, but the largest source of CO2, the largest emissions of all the emission types would likely be from the CO2 generated by the gas turbine to generate the electricity that was needed to power the FPSO. So, as I mentioned, oil companies in the UK are required to reduce those emissions. So they're required to do something. So let's imagine that you have a FPSO barge. It's 200 miles offshore in 6,000 feet of water. Where are you going to get electricity to that to power it? That's not coming from the natural gas. That's green, clean electricity. Well, we've seen Equinor, formerly Statoil, has done some interesting things. They've actually provided power from shore from their abundant hydroelectric power, brought power to shore to offshore floating platform. But that's not deep water and it's not 200 miles offshore, all right? But Equinor also has built the largest floating wind farm in the world, and it's used to power about 35% of a collection of FPSOs and rigs in the North Sea. So if you try to investigate wind power as an option, immediately you get into the power that the amount of power, the amount of energy that wind power would be producing is not going to match the relatively steady load that's needed on the FPSO. You know, there's a huge variation summer to winter typically for wind, and there's no way you're going to have batteries storing power for summer to wind. And there's no way you're going to have hydrogen easily doing that. You can't have such a big vessel of hydrogen. And there was one other option I think one time we looked at was you could actually compress air to the ocean floor and use compressed air energy storage as another way of storing. But all three of those are very, very pricey. So what other ways might there be? All right. So let's take a look at some of the options that, you know, we had brainstormed. And power from shore. Now you suddenly could put gas turbine with carbon capture and storage, all right? And then take that carbon and re-inject it in the CO2. The distinct advantage of this is that the natural gas was going to be re-injected down into the ground already. So typically, my rough rule of thumb is a natural gas power plant with CCS is roughly 30% more expensive to build because of the methylethylamine and the absorbers and the regenerators and all the carbon capture, all right? Than a conventional gas turbine. And it also would use roughly 30% more gas to make the same amount of power. But using more gas to make the same amount of power is not a particularly problem for most of the FPSOs because that gas was just re-injected down there. So that basically the cost of that gas is virtually zero. And that turns out that this looks like it is a fairly popular option because we've seen new FPSOs recently ordered by both Petronas and Petrobras that are being ordered with carbon capture and storage. That's the solution that these oil companies have decided. Other oil companies may decide something different. So offshore floating wind farm, maybe, you know, and that might be able to have some possibility. One of the other, we started brainstorming wild and crazy options, you know, because, you know, some oil companies really say our shareholders are demanding we're going to do something, we're going to spend money, all right? And some of them actually have some money to spend from what I understand, all right? So one of the other options was floating nuclear power plants, all right? And you see in the bottom right picture, there is a Russian Arctic floating power plant. It's a nuclear propulsion vehicle, but it also has a nuclear power plant meant to export power, all right? And China has declared that China had actually built the ship for this, and China is very interested to build multiple of these ships with their own nuclear plant floating on it to power their FPSOs. All right, so China has an active program to actually put nuclear reactors and power their FPSOs. All right, floating solar, wave, these things are probably not going to work too well. You could export green power out there, but you know that's a pretty pricey activity, and offshore storage for wind is also extremely pricey practice. You know, so I guess you kind of see that the direction that we've seen them go is if you're close to shore, you can bring power from shore. You know, you might be able to put wind to supplement that. Really, the CCS technology, the floating nuclear, is quite a ways off. There's a company, Seaborg, that actually is trying to develop offshore floating power plants. And there's several dozen offshore floating fossil plants that can be moored off cities to power cities. And that's not an uncommon thing. It's not super common, but. So this chart came from OECD and IEA, International Energy Association, and basically it kind of showed a summary of all the emissions upstream, midstream, and downstream. It might have helped you with the Slido show if I'd have showed you this sooner, but you probably had that pretty good idea anyway. All right. So in any event, fugitive emissions are shown pretty high here. This is a worldwide situation, but you know, extraction and drilling, flaring, CO2, and then crude transport. And fugitive emissions, refineries, you know, steam and power, you know, is a big use. I've heard the rough estimate that refineries need to burn about 5% of the crude oil, energy-wise, to process all of the crude oil into finished products. I'm not sure that could vary from refinery to refinery. Emissions from U.S. refineries, where does it come from? All right. The most of it comes from combustion, and if you've ever visited a refinery, there's a lot of devices that are burning fuels. You know, you could be making hot oil or steam for general heating distribution. You have a lot of fired furnaces. The FCC with the coke burn-off is actually another very large one. I didn't realize just how big that was. A sulfur plant making hydrogen. Hydrogen is a definite chunk. Right? Maybe it's possible to import power to make green hydrogen, all right? And so that little segment might be possible to alleviate.